Let's go ahead and talk about some gas laws. So which statement describes the particles of an ideal gas based on the kinetic molecular theory? So remember, kinetic molecular theory says that particles move in a constant, random, straight line motion. They have negligible volume and they have negligible intermolecular forces. And lastly, when they collide, their energy, the overall energy still remains the same. They just transfer their energy from one body to the other. So if you look at these options, the volume of the particles is considered negligible. That is something that kinetic molecular theory said. Forces of attractions are strong. Not what KMT said. Particles are closely packed. Not at all, because they are gases. Particles are separated by small distances relative to their size. This is similar to number 3. And again, particles have a huge distance between them. According to kinetic molecular theory, ideal gas particles are separated by small distances. No, do not transfer energy when they collide. They do have attractive forces. No, kinetic molecular theory said they have negligible intermolecular forces. They do move in random, constant, straight line motion. According to kinetic molecular theory, an ideal gas has particles with large volume, large atomic nuclei, no attractive forces, no random forces. That will be, no random motion. That will be no attractive forces. At which temperature and pressure will a sample of neon gas behave most like an ideal gas? So remember, kinetic molecular theory said an ideal gas is something that has no volume and no IMFs. So the only way that a gas can behave like an ideal gas is if it has very little volume or very little intermolecular force, which is only possible if, and you must memorize this, so this is only possible when we have very, very high temperatures, because now the particles are moving very fast, so they have very little attraction between them, and it's hard for them to occupy any space because they're just all over the place. And then if we also have very low pressure, now there's a lot of distance between the particles, so we can't really say what is the volume of the gas because it's not occupying the entire space. And also because they are so far away from each other, they have little to no intermolecular forces. So we are looking for the highest temperature and the lowest pressure in this case. So that will be option 3. State one change in temperature and one change in pressure that will cause the gas in a cylinder to behave more like an ideal gas. That is this answer that we just wrote. At STP, which gas has the same number of molecules as 2 liters of CH4 at STP? So remember, according to Avogadro's law, if we have 2 gases at STP, no matter what those gases are, their volume is going to be the same. So we are looking for any gas that has the same volume. So your answer will be 2 liters. Which 2 samples contain the same number of molecules? So once again, according to Avogadro's law, the gases that have same volume have same number of molecules. Doesn't matter what gases they are. So gas number 1 and gas number 3, they have same volume. So that means they have same number of molecules. 2.5 liter sample of SO2 gas at STP and a 2.5 liter sample of carbon dioxide at STP can be differentiated by comparing their so they are 2 different gases, but they are both at STP and they both have the same volume. So how can we differentiate between them? If we compare their masses, there's no information about the masses, so we don't know. Their phases are the same, their temperatures are the same, and their volumes are the same. So coming back to the masses, what we can assume is that they are talking about the molar masses here. So because they are different gases, they are going to have different molar masses. So that is something that we can use to differentiate. At STP, which property can be used to differentiate 1 mole sample of chlorine and krypton? So their phase, no, because they are both gases. Pressure, they are both at STP. So no pressure, no temperature. So we can go ahead and compare their chemical reactivity because krypton is a noble gas, so it doesn't react. Which graph represents the relationship between pressure and volume for an ideal gas at constant temperature? So remember that pressure and volume are going to be, according to Boyle's law, when we increase the pressure, the volume decreases, because now we have less space. So there's an inverse relationship, indirect relationship between pressure and volume. And just remember that that indirect relationship is not going to be a linear line. It's this exponential function. All right. I apologize for my neighbor's dog. So explain in terms of particle volume why the volume of helium cannot be compressed by the piston to zero volume. So you can say, to answer this question, that the particles are going to occupy some volume, even if it's very little, but as long as there are some particles, they do occupy some space. State what happens to the average distance between the helium atoms as the gas is heated. So when we heat the gases, we are increasing the kinetic energy. So average kinetic energy increases. And so the particles are going to move more vigorously, and the average distance is going to increase, of course, if they have more space. But you can just in general say that the average distance between the particles is going to increase. State what happens to the average kinetic energy of the gas particles if the cabin temperature decreases. So if temperature is decreasing, average kinetic energy is also going to decrease. Particles start moving slower. Show a numerical setup for calculating the pressure in the submarine cabin if the cabin temperature changes to 293 Kelvin. So it looks like we are comparing the temperature and the pressure. So according to, if you don't remember the equations for each gas law individually, you can always use the combined gas law. Just ignore the thing that is not changing, and plug in the values for the things that are changing. So what we do know from the question is that okay, so this right here is actually 2.4 times 10 to the power of 5, which is actually about 240,000 liters. So as people in the cabin breathe, carbon dioxide gas can build up to safe levels. Okay, so it doesn't look like, according to the passage, the volume is changing, so we can just ignore that. The temperature was initially 312, and now we changed the temperature to 293. So let's go ahead and plug in the temperatures. Initial was 312. Final is 293. We need to know the final pressure, and the initial pressure was about 116. So you can just go ahead and solve for x, or leave it like this because it only asks for the numerical setup. So convert the original air pressure in the cabin of the submarine to atmospheres. So remember, 1 atmosphere is equal to 101.3 kilopascal. This is something that you should memorize, but you can also get this information from table A. So you can just use dimensional analysis, multiply 2.4 times 10 to the power of 5 with, so this is, I used the wrong thing. I used the volume. You should have 116 kilopascals. So multiply this with 1 atmosphere is equal to 101.3 kilopascal. So just do the division and get your answer. State in terms of average distance between the helium atoms why the density of gas increases when the piston is pushed further into the rigid container. So what happens is that when you are pushing, when you are increasing the pressure, remember that the equation for the density is mass over volume. So when you are increasing the pressure, the volume decreases, but the mass stays the same. So to answer this question, you can just say the mass stays the same, but the volume decreases, which is why the density increases, because density and volume, according to this equation, are indirectly related. Compare the number of helium atoms in the cylinder at a pressure of 0.5 atmosphere to the number of helium atoms in the cylinder when the pressure is increased to 1.5 atmosphere by pushing the piston. So in this case, we are comparing the number of atoms with the pressure. So here's the thing. We are only changing the pressure, but we are not adding or removing any helium atoms. So to answer this question, you actually don't have to do any math because it's the same number of atoms, as long as you're not removing any atoms or adding any. So determine the volume of a sample of carbon dioxide if the temperature and pressure are changed to 336 and 152. So this is an example of something where all of the quantities are changing. So you can use the combined gas law. So P1V1 over T1 equals P2V2 over T2. So plug in your numbers, get the answer. Compare the mass of original 200 milliliter sample of carbon dioxide to the mass of the carbon dioxide sample when the cylinder is adjusted to a volume of 100 milliliters. So in this case, we are comparing. Once again, this question is kind of similar to number 17. The mass of the sample is not going to change unless we are adding or removing any gas. So you can simply say that the mass is going to stay the same in this case as well.